Hi. So I'm hoping that my audio is better in this video compared to others because I bought a microphone. You can see it here. Super excited, moving up in the world when it comes to making these videos. What I wanted to do for this video is go over the concept of Taylor series, as I know that when you took calculus, it probably was confusing. It was very confusing for me when I took Calc 2 in the past, but I'm hoping that this video clears up some of the confusion. And what I show on the screen here is the Taylor series expression, which says f of x plus h is equal to f of x plus f prime of x times h plus f double prime of x times h squared over 2 factorial plus f triple prime of x, h cubed over 3 factorial, and so on. What does this mean? Now, in the picture I have here, let's say that I have some known point. And the example I'll give to make it somewhat physical is, let's assume that I am throwing a paper airplane. Assume I'm throwing paper airplane. Now, the reason that I chose a paper airplane is that it's kind of unpredictable. If you throw a ball, you know it's going to have some sort of arc, parabola type of behavior. But with a paper airplane, if you throw it, depending on how it's made, maybe it's smooth, maybe it just goes up and comes back down. The point is, we don't really know. And maybe I'm curious, if I know the general behavior of what the airplane's going to do, where is it going to end up 5 feet away from me? So let's say that this known point is my starting point. Maybe this is where I'm standing. Maybe I'll make it bigger. I'm standing, and I go to throw this paper airplane. I know where it is at my initial starting point. And I'm trying to figure out, okay, where is it going to end up 5 feet away from me? So let's say that this is my starting point where I'm standing, and this is, let's say 5 feet away. Where that h would be 5 feet. That's how far away it is relative to where I currently am. And I drew an example here, like maybe the trajectory is this blue type of line. I drew this dash line because I don't know for sure what it is. And then maybe it ends up at this height here 5 feet later. We don't know. The idea of a Taylor series is that if you take the behavior or what you know about your starting point, you can get a better prediction for where your function is going to end up later down in x. And we will get the exact value of that function. We get exact value of the function at the new point, which again is f of x plus h. That's the value of the function f of x plus h at the new point, which is x plus h. If we know everything about the starting point. What do I mean by that? Well, this expression is exact for an infinite number of terms. And I'm saying that lightly because depending on the function, maybe a lot of the other terms are 0. But in the most general case, we will assume that f of x plus h will be exactly correct if you had an infinite amount of these terms, f of x, f prime of x times h, so on. So what I'm interested in is knowing everything about that starting point, which means I need to know what the function value is at that starting point. I need to know the first derivative. This is the same as the slope. At that point, the trajectory, that initial slope of the tangent line at that point, the concavity, at that point, and then several other things. If I know all of the behavior at my point, I can predict what's happening. And let's look at the cases where we don't know everything that's happening and kind of see how that translates. So I'm going to go ahead and I'm going to take this graph here and see what I can grab nicely. Let's copy this. We're going to do some examples of this. And that's our known point. And let's say we have a one-term Taylor series. That says that f of x plus h will be approximately equal to f of x. If you come back here, basically what I'm saying is that we're ignoring all of these terms and just saying that we're going to approximate that new function value by saying it's equal to the current function value at our known point. What does that look like for our paper airplane? Well, I'm saying that no matter what h is, I'm just going to assume that this is just going to travel in a straight line across. Is that accurate? For our paper airplane, probably not, depending on how far away the launch is from, or how far away you're looking at relative to the launch. But this is true. This is true for all h. Which means that if I go 20 miles down from where I threw the paper airplane, it's still going to have this flatward trajectory, which is not accurate. So having one term in our Taylor series doesn't really do us a whole lot of justice because we don't have enough information about our starting point to have an accurate representation of what our paper airplane is going to do. Let's try this again. Let's go ahead and do this again. I'm going to paste the same exact thing. And now let's say I do a two-term Taylor series. This is f of x plus h is f of x plus f prime of x. Oops, I'm going to move this down a bit. Plus f prime of x times h. And let's think about this a little bit. This f prime of x is the derivative or the slope at the starting point where we threw the paper airplane from. And if you think about this in terms of high school algebra, where instead of dealing with f of x and f of x plus h, remember that those are y values. Maybe this is some y value, at the faraway point. That's a y value at the current point. F prime of x is the slope. And then h is how far away you are from that current point. And really all we did was rearrange the slope equation. If I do y2 minus y1 is equal to m times h, and then divide by h, that's just the slope. So what we're saying is, okay, I'm going to approximate the value at my new position 5 feet away by taking my current value and using this derivative to determine what it's going to look like. Maybe the slope of this line, let's go ahead and erase some stuff here. Maybe the slope at this line looks something, let me do it dashed, looks something like this. we see that this has a constant slope. So we have some information because this slope is found at our starting point. So basically, if you think about the paper airplane, if I were to throw it up, before I let go, I have this upward trajectory. I have an idea of where this thing is going to end up. Just knowing the general way my arm is set up to throw it. Maybe I'm throwing it down, maybe I'm throwing it straight, or maybe I'm throwing it up. And depending on the way I'm throwing it, I can go ahead and estimate this is where the plane is going to end up some distance away. Now, if h is small, this is a pretty good estimation. And just thinking about the paper airplane, thinking about the paper airplane, if I were to throw it up, and here I am again, I'm going to throw it maybe to do this general thing, and then maybe it does some crazy stuff later on. But if I zoom into this region here is basically a straight line. So if I were to be interested in finding what the position of f of x plus h is at some tinier h away, that might be pretty accurate. And the reason why is if we come back up to the total expression here, for small h, all of these terms over here are basically really tiny. Which means that if those are negligible, we can say that f of x plus h should be approximately, would be approximately equal to those first two terms added together if h is small. But now if h is big, and I'm really interested in something very far away, that means I need to know the higher order derivatives. Because all we're doing is trying to predict where our function is going to go relative to our starting point. If we have an idea of what's happening at the starting point, we know the slope there, we know the concavity there, we know the third derivative, fourth derivative, fifth derivative, etc. As h gets bigger, if we have those terms, we have a more accurate prediction about where our function is going to end up. Because at the end of the day, I'm going to go ahead and say that the accuracy of this depends on how many terms I have and how much information I have at my known starting location. As I already showed, if you have one term, that's basically saying the y value far away from us is going to be exactly the same as the y value where we started. Again, that's basically neglecting all of this. If I were to include two terms, now I'm neglecting concavity and all the other higher order derivatives, but at least I have a slope. And with that slope, I can get an idea about where this point is going to go based on how I launched it, paper airplane. But that's really good for small h. As we make h bigger and bigger, these terms do not become negligible anymore. So then perhaps we say, okay, I want to include three terms. Now, not only do I know the slope, but I know the general concavity of it. So if I were to go ahead and paste this one more time, now I have the idea of, okay, I know what the slope is here. Oops. I know what the slope is here, but I also know it's going to have some negative concavity, possibly. And I can get a better estimate about where my object or my paper airplane is going to be some h away from where I am. So this is really useful when it comes to finding the values of functions at some faraway location or at some obscure location. I think the example I have in my notes set is the idea of finding sine of some really random angle. Because we know the unit circle, sine of 0, sine of pi over 2, sine of pi, like those are easier type of calculations. But if I say, what's the sine of 3 pi over 17, well, that's a little bit more complicated. But if we go ahead and take what we know, maybe we know what's happening at sine of 0. We should. And then we say, okay, we're h away. Let's take all the information we have about the function being a sine wave and use that to estimate what's happening at that 3 pi over 17 or whatever arbitrary angle you're thinking of. I think I'll save some examples for another video, but this video is strictly to hopefully elucidate what is happening with the Taylor series behind the scenes. If you have questions about this, please let me know. Otherwise, I will talk to you soon. Okay, stick around for the next video. Thank you.